Section 3, Aeroelasticity in ZAERO. Aeroelastic response of a flight vehicle is a result of a mutual interaction among inertial forces, elastic structural forces, and aerodynamic forces induced by the structural deformation, as shown in this equation, where mgg and kgg are the mass and the stiffness matrices in the G set, and x is the structural deformation, also is in G set. The F can be split into two parts. The first one we call aerodynamic feedback forces, which is induced by structural deformation, is shown by the F sub A, which is a function of x, and the external forces. And the typical example of external forces is the gas force, stall ejection forces, trim forces, or the control surface aerodynamic forces due to pilot input command or command from the control system. So F sub A is an aerodynamic feedback force due to the structural deformation. Aeroelastic problem is due to the aerodynamic feedback force. If there's no aerodynamic feedback force, the equation of motion is reduced to the force structural dynamic problem, and therefore for the force structural dynamic problem, there's no instability problem. And when the structure deforms, and it can induce aerodynamic forces, but these forces does not react instantaneously. Rather, it has an aerodynamic lag effect. So this can be shown by the Wagner's function. So the lift coefficient normalized at 2 pi of a 2D airfoil due to an impulsively increased angle attack from 0 to 1 in incompressible flow can be shown by the Wagner's function. And we all know for the steady aerodynamics, the steady lift of a 2D airfoil at a unit angle attack computed by the exact steady aerodynamic theory is 2 pi. But however, the Wagner's function showed the lift does not instantaneously reach 1. The normalized lift reach 1 only at a t equals infinity. So this effect is called aerodynamic lag. Because of the aerodynamic lag, the aerodynamic forces acting on the structure could amplify the structural deformation, leading to aeroelastic instability, such as a flutter. So when, for example, if you have a structure moving up, and due to the lag effect, the lift also could acting upward, and which amplify the structure motion. And the aeroelastic system can be shown by this diagram. So you have an equation of motion for given external forces, and the structure will deform. This deformed structure can induce aerodynamic feedback force. So this feedback force will be added to the external forces. And so because it is a kind of a closed loop system, it could be unstable. And so if we want to know where is the instability boundary, namely the Flutter boundary, and all we need to know to do is to give the system a very small disturbance epsilon. Then we calculate the response. If the response is the divergent response, and then we know we have a Flutter problem. But if we found that the flight condition is below the Flutter boundary, so the system is stable, then we can give an external force such as gas. Then we can calculate the gas response. And so this is a dynamic response problem. And F sub A is usually very difficult to be measured in the wind tunnel. So it's generally provided by the computational aerodynamic method. And in general, f sub a could be nonlinear with respect to the structure deformation. However, if the structure oscillation amplitude is assumed to be small, and then the aerodynamic force varies linearly with respect to x. This is called amplitude linearization. So, for example, if we look at the CL versus angle tag curve, and at a low angle tag, the CL curve usually is a straight line. That means the system is linear. Okay, so if the system is linear, it can be recast into a transfer function that relate f sub a to x if it is in time domain, is by means of a convolution integral. So if h is a multi-input and multi-output aerodynamic transfer function, and if we have a structure deformation, and to calculate the aerodynamic forces, and we just solve this convolution integral, where Q infinity is the dynamic pressure, L is the reference length, is generally defined by the half of the reference core, and V is the free string velocity. But if we apply Laplace transform to this convolution integral, then we have a much simpler form. So h bar here is the Laplace counterpart of h, and so if we have a structure deformation in the Laplace domain and multiply by the h bar, and it will give us the aerodynamic forces in the Laplace domain. Okay, so once we have the AIC matrix, okay, in the matrix form, h bar is called aerodynamic influence coefficient, AIC matrix. Once we have AIC matrix, we can use AIC matrix to rapidly generate various kind of aerodynamic forces. If we have a structure deformation, we can calculate the aerodynamic forces due to structure deformation. Then if we have a control surface deflection delta, and AIC multiplied to the so-called the control surface kinematic mode, and that will give us the aerodynamic forces due to control surface deflection. Now, if we want to calculate the gas load, and AIC multiplied to the gas induced angle tag, and then times the gas velocity, that will give us the aerodynamic forces due to gas. So AIC is a multi-input, multi-output aerodynamic transfer function. AIC is independent of input, so independent of structural deformation, control surface kinematic mode, and gas. So if the aerodynamic model is unchanged, AIC matrix can be only computed once and reused for different input to rapidly generate aerodynamic forces. And now, because the finite element model could be large, and so the GZ degree freedom can be in the order of thousands, if not millions. So to solve this large size problem, it takes a lot of time. So in order to reduce the size of the problem, we introduce so-called modal approach, and we assume the structural deformation and can be superimposed by a set of a lower order natural mode. So this is what we call a mode shape matrix, and C is a so-called generalized modal coordinate. So for a single wing structure, probably only is 10 mode, and for whole aircraft, probably we need somewhere around 50 to 100 modes are sufficient. So we can reduce the problem size from thousands to just below 100. And then if we substitute this equation into the equation of motion, we can have this equation, where MHH is the generalized mass matrix, which is the GZ mass pre and post multiplied by the motion matrix, and KHH is the generalized stiffness matrix, which is the KGG times pre and post multiplied by motion matrix. QHH is the generalized aerodynamic force GAF matrix due to structural deformation, which is AIC matrix pre and post multiplied by the motion matrix. And QHC is a GAF due to control surface deflection, which is AIC times the control surface kinematic mode and pre-multiplied by the transpose of the motion matrix. And QHG is a GAF due to gas, is AIC times the gas-induced angle attack, and then pre-multiplied by the motion matrix transpose. So the GAF are the key element to solve for various aeroelastic problems. For example, if we set the right-hand side of this equation to be 0, and this becomes an eigenvalue problem, and we can treat as the Laplace variable as an eigenvalue, and whose real part is a damping, imaginary part is frequency, and if the damping changes sign, that's where the flutter occurs. Okay. Now, once if we found out the flight condition is within the flutter boundary, which is stable, then we can perform the dynamic loads problem. So we give a control surface deflection, we can calculate the structure response, or we give a gas velocity, the gas profile, and also we can calculate the structure deformation. And to generate the AIC matrix, and ZAERO has 5 aerodynamic methods, namely Zona 6, Zona 7, Z-Trans, Z-SAP, and Zona 7U, that jointly generate the AIC matrices covering the complete domain of a Mach number range. So Zona 6 is for subsonic, Zona 7 is for supersonic, Z-SAP is for sonic Mach numbers. And those 3 methods solve the linear unsteady potential equation. Therefore, there's no nonlinear aerodynamics effect. Z-Trans solve the linearized transonic small disturbance equation using the field panel method, and the linearized transonic small disturbance equation contains the varying coefficients, and those varying coefficients is a steady flow. So we call steady background flow, and the steady background flow is imported from the CFD solution. And we have Zona 7U for hypersonic unsteady aerodynamics. And all methods adopt the panel method to solve the integral equation of the potential equation. So first, we have to discretize the aircraft into many small boxes or panels. Each aerodynamic box contains a control point where the boundary condition is imposed. All methods solve the frequency domain unsteady aerodynamic equation in the context of the simple harmonic motion, which is based on a fundamental unsteady aerodynamic parameter called reduced frequency, and K. And the K equals omega times L divided by V, and omega is the harmonic oscillation frequency. So usually, so the AIC matrix is a square complex matrix, which with a size equal to the number of panels in the model. So in the ith row of the GS column in the AIC matrix contains the unsteady aerodynamic forces on the ith panel due to a unit input at the control point of the GS panel. So therefore, the AIC matrix contains the purely unsteady aerodynamic characteristics of the aerodynamic geometry, and therefore is independent of the structure. And so, if we have a structure deformation and defined in K set and multiplied by the AIC, that will give us the aerodynamic forces in the K set. And so AIC is independent of structure, depends only on the aerodynamic panel model, the Mach number, and the reduced frequency. And for Z-Trans method, it also depends on the CFD generated steady background flow. And once generated, it can be saved and retrieved for structure variation. So if you during the structure design loop, you can reuse the AIC if the aerodynamic configuration is fixed. And so the AIC is solved we need a set of AIC at various reduced frequency, and the reduced frequency, the number of reduced frequencies usually is less than 10. Okay, so usually n equal 10 is sufficient to capture the variation of the flow unsteadiness in the frequency range of inches. Okay, so each AIC leads to a set of GFs, QHH, QHC, and QHG. And so during the aeroelastic computation, at any given reduced frequency, we can interpolate the QHH, QHC, QHG from those computed GAFs at those reduced frequencies. And then we need a spline. Okay, a spline matrix. Because AIC is computed based on the panel model, which is in general considerably different from its respective structural finite element model. This gives rise to the problem of displacement and force transfer between these two models. The problem of data transfer between the panel and the structural models usually amounts to the displacement transfer from the structural grid points to the aerodynamic control points of the panel model. And after the aerodynamic method computes the aerodynamic forces on the panel model, we needed to transfer those forces from the aerodynamic model to the structural grid. So ZAERO provides a spline module that generates a spline matrix we call G sub kg. So once you have G sub kg, you have a structural deformation in the G set, and multiplied by the spline matrix, that will give us the structural deformation in the K set. K set is 6 times the number of aerodynamic panels, and because each panel has a 6 degree of freedom. And we have 4 methods incorporated in the spline module, namely the beam spline method, infinite plate spline method, thin plate spline method, and the rigid body attachment method. These 4 spline methods jointly construct the spline matrix G for displacement transfer. Now, if you want to transfer the aerodynamic forces in the K set back to the structural G set, and all you need to do is to use the transpose of the spline matrix, and based on the principle of virtual work, one can prove the force is conserved. Meaning, if you sum all the force along the x, y, z direction from the K set, then after you transfer the force to G set, you also sum the forces along x, y, z, and you will find out those 3 sets of forces that they are equal. Okay, this is guaranteed by the principle of virtual work. The AIC matrix and the generalized aerodynamic forces matrix can be transformed to the structure G set and the H set. Okay, so if you have a structure deformation in the G set and go to the spline, you will give us in the K set, and multiply by the transpose of the spline matrix, we will transfer the forces back to the for the G set. And then if you want to calculate the GAF, and you use AIC pre and post multiplied by the spline matrix, and also pre and post multiplied by the motion matrix, that will give you QHH matrix. And the harmonic motion assumption in the unsteady aerodynamic method implies that the QHH is valid for steady state response of the structure with no divergent or decay motion. And this implies that for Flutter analysis, the solution is valid only at damping becomes 0. And for transient response analysis, it is required to transform the QHH from the frequency domain to the Laplace domain. And in order to obtain the Flutter solution at non-zero damping, the G method Flutter solution technique approximate the Laplace domain GAF equals the frequency domain GAF plus G times particle Q particle IK. G is the non-dimensional damping. Okay, and for dynamic loss analysis, ZAERO adopts the rational function approximation to transform the frequency domain GAFs to the Laplace domain. And so, if we have a Laplace domain aeroelastic equation of motion and go to rational function approximation, and we can formulate a state space equation of the open loop aeroelastic system, where x sub ae is the state vector, and it contains c dot and x sub a. X sub a is a vector of aerodynamic augmenting states arising from the rational function approximation, and u sub ae contains delta dot, and W2 contains the gas velocity and gas acceleration. Now, if we can formulate the control system into a state space equation, we can easily combine the state space equation of the control system and the aeroelastic system to have a closed loop state space equation where x sub v contains c dot, x sub ac. X sub ac is the actuator states. X sub c is the control system states. Okay, in ZAERO, we can perform the Flutter analysis in frequency domain or in the Laplace domain. So we can go to the state space for analysis for both open loop and closed loop. And we can perform frequency domain and the time domain gas analysis for both open loop and closed loop. And we can perform maneuver and the ejection loss analysis for both open loop and closed loop. And we also have a nonlinear Flutter analysis module, which is similar to the maneuver and ejection loss analysis, but includes the structural nonlinearity, such as free play or friction. And the last module is called trim module. A trim module solves the static aeroelastic equation and calculates the trim load. So F sub A is the aerodynamic forces, F sub I is inertial forces. So the net force at a trim condition and applied to the structure, then we can calculate the structure deformation due to trim load.